Imagine it's 1972. The Apollo missions have conquered the moon, but NASA's next dream is even bolder: a reusable spaceplane, the Space Shuttle. This wasn't just another rocket. It was a glider the size of a commercial airliner that had to land on a runway. But the biggest challenge wasn't the heat shield or the engines. It was the software. How do you write code that absolutely, positively cannot fail when human lives are on the line? This question led to the creation of the software production facility at the Johnson Space Center. Inside, a team of brilliant engineers, led by legends like John Aaron, faced a task that seemed impossible. They weren't just writing code, they were building a digital lifeline. Every command, every calculation had to be perfect. The central question they wrestled with every single day was, how do you write code meant to keep humans alive with zero room for error? Their answer would change software engineering forever. To achieve this, NASA developed a philosophy that was completely alien to the fast and loose coding culture of the time. They treated software not as a set of instructions for a machine, but as a life support system, as critical as the oxygen tanks. The process was defined by absolute, uncompromising rigor. Every single line of code was subjected to a brutal gauntlet of peer reviews, simulations, and verifications. Think about that. Not just functions or modules, but every single line. This meticulous process meant that a single developer might only write a few hundred lines of approved code per year. They were nicknamed "Wanan, the highest paid clerks in the world," because so much of their job was paperwork, checking, double-checking, and documenting everything. They used a principle called formal methods, using mathematical proofs to verify that the code would behave exactly as intended under all possible conditions. There was no move fast and break things. The mantra was, move slow and break nothing. This wasn't just about good practice. It was about creating a system so reliable that astronauts could bet their lives on it, and they did for 30 years. So, what did this nearly perfect software actually do? Everything. The primary avionics software system, or PAS, was the central nervous system of the space shuttle. It managed the entire flight, from the violent ascent into orbit to the delicate, unpowered glide back to Earth. This software controlled the 5 main computers, which ran in a redundant set. 4 computers ran identical software, constantly voting on every decision. If one disagreed, it was immediately voted out. A 5th computer ran a completely separate, independently developed backup system, just in case the primary software had a hidden, catastrophic flaw. The code was responsible for guidance, navigation, and control, firing the thrusters with pinpoint precision to adjust the orbiter's path. It managed the main engines during launch, throttling them up and down to avoid putting too much stress on the vehicle. It controlled the robotic arm, the payload bay doors, and countless other systems critical to mission success and astronaut safety. And here's the truly mind-blowing fact. Over the entire 30-year history of the Space Shuttle program, with 135 missions, there was only one known software bug that occurred in flight. It was a timing issue that was resolved within seconds and had no impact on the mission. The code was so clean, so robust, that it remains the gold standard for safety-critical systems today. Now let's talk about the human cost of this perfection. Imagine being one of those engineers. You go to work every day knowing that a single misplaced semicolon or a logical error could have fatal consequences. The pressure was immense. These weren't just abstract problems, they were life-or-death equations. The team fostered a culture of mutual responsibility, where calling out a colleague's mistake wasn't an insult, it was a duty. It was an environment of intense intellectual honesty. This raises a fascinating ethical debate. Can perfection truly exist in software? The shuttle team got closer than anyone before or since. They proved that with enough discipline, resources, and time, you can create software with a reliability that borders on absolute. But it makes you look at today's world of software development and wonder, has our modern culture of rapid releases, constant updates, and good enough patches lost the discipline that NASA once demanded? We accept bugs and crashes in our phones and computers as normal. But the shuttle program reminds us that when the stakes are high enough, a different standard is possible, a standard of perfection. So where did all this incredible work go? Is it just a museum piece? Absolutely not. The legacy of the Space Shuttle's software is alive and well. The principles of redundancy, rigorous verification, and formal methods are the bedrock of modern aerospace engineering. Every time a SpaceX Falcon 9 lands itself or a Boeing Starliner docks with the International Space Station, they are standing on the shoulders of the shuttle's software pioneers. The DNA of that meticulous, safety-first approach is embedded in the flight control systems of virtually every modern aircraft and spacecraft. But the future presents a new challenge. We are moving into an era of more complex, AI-driven, autonomous systems. These systems learn and adapt in ways that are not always predictable. Can a neural network ever provide the same level of mathematical certainty that NASA's handcrafted code did? That's one of the biggest questions facing engineers today. How do we ensure the reliability of systems that, to some extent, program themselves? The future of spaceflight will undoubtedly be driven by new technologies and artificial intelligence. But the foundation, the core understanding of how to build software that you can trust with your life, was written decades ago by the incredible team behind the Space Shuttle. Their code didn't just fly a machine, it flew humanity, and its echoes will continue to guide us as we reach for the stars. Thank you so much for watching. If you found this journey into the world of space-grade software as fascinating as I did, please hit that like button and subscribe for more stories from the history of science and engineering. Let me know in the comments what other incredible feats of engineering you'd like to see covered. See you next time.